Archiving started.
Okay. Yeah, what we could do is I can share the desktop, and then we can, look at the website. Are you able to look at the website on your own?
Yes, I am.
Okay. Yeah, I'm trying to think. I think it would take too much time if I wanted to load individual images. So let me just go ahead and, share my desktop with you, and then we'll just go to the lab.
Okay.
Just going to take a moment.
That's fine. Did you know that they didn't allow us use calculators on the finals?
Yeah, I heard about that. Maybe I haven't communicated that clearly. Yeah, I'll take that into account. I'll probably put a lot more weight on the lab final that we do online, than this assessment anyway.
That would be helpful, because I really wish that they would have left. I don't understand why, because at one point they said so, and then at the last minute they were just like, no.
Yeah, I mean, the problem really is with these proctored exams that, they have to be held under exactly the same circumstances on every campus, so that no one can complain. And, that's why when it is not specifically stated what students can use, they just have to go by the default, paper, maybe scratch paper, but only a pencil and an eraser, I guess. Yeah, I mean, I'm hoping that in the future we can move those exams into the computer lab, so that you can take them online. But, I mean, it'd still be proctored, and you'd still have to come to campus, but at least, you'd be in a computer lab and not in a gymnasium. Well, yeah, do you see my desktop now?
Yes, I can see the part that it says update sharing and intern.
Okay, I'm going to minimize that, and I'm going to minimize our screen here. And I'm going to go to the Moon Lab. Okay, and I'm going to go to the Moon Lab images. Okay, so that's item 4 in the table of contents. Okay, how far have you gotten so far in the Moon Lab?
I've gotten the first page done.
Okay.
And then I just wanted to kind of go over.
Okay, all right.
But I also wanted to for estimating the fraction of the Earth side of the Moon, that is Maria.
Okay, yeah, we can.
I'm
sorry, go ahead.
Oh, well, for number 2, I found about 12 to 14. I laid the goals all over. But when it came down to estimating the fractions.
Yeah, it's sort of, okay, let's go to the image of the near side of the moon. And, yeah, you should probably sort of eyeball it because, we're seeing a three-dimensional half sphere as a two-dimensional image. So, we're not seeing the actual area anyway. But it turns out, in a view like that, mostly the polar regions might get a little bit shortchanged. So, I mean, what would you say? Is it more than half, a little bit less than half?
I would say about a third of it. Or maybe
a
third of it.
Well, a third. A third would be a pretty good estimate. So it's between 30 and 40%. So if you say a third, that's right in the ballpark.
Okay. I was thinking that, but I just wanted to make sure.
Yeah, that would be kind of hard. I mean, unless you had some sort of, computer program that could count pixels. Okay, so yeah, third would work for that. Okay, and then what do you have for the general shape of the Maria?
That is flatted, volcano areas.
Yeah, what kind of geometrical shape would it be? I mean, if you had to choose between, like square or rectangle or circle or...
Circle?
Yeah, they're mostly circular. But there's one major exception. Yeah, if you look to the north, that is Mare Frigoris up here, and that is more, like elongated. I mean, that is not quite as circular as the others. So that's the one that you want to put down there.
And it's pointing to the area north. Right.
Yeah. Yeah. Do you see my little magnifying glass here with a plus on it?
Yeah, I can see it now. I have the bottom of the screen on, so I have to pull up.
Oh, okay. Yeah, that's right. Your window might be a little bit smaller than. Yeah, so up here, the Mare Frigoris is more lengthy. It's not quite as circular as the other ones. But in general, the shape is pretty circular. So right here you see that most of them are pretty circular in nature. And here just a whole bunch of them together, so basically overlapping circles at that point. Okay, now you're okay with the wrinkle ridges?
Actually, I did not see the wrinkle ridges.
Okay. See, I think I'm gonna have to go back to the images. Here's the near side with labels. So let's just quickly go up here. And this northern Mare here, Mare Frigoris, that's the one that's not quite circular. Okay, so let's go to the wrinkle ridge. Okay, so if we go to the Mare Serenitatis, wrinkle ridge, well, it's sort of like this squiggly line here, that's sort of sinuous, and goes from north to south. Well, what would you estimate its longitude to be?
10 degrees?
Well, if it's between 20 and then going over to 30.
Well, 5.
Yeah, so it would be like 25 degrees, because it's pretty much smack in the middle.
That's how you count it.
Yeah, so 20, and then you would, 21, 22, 23, 24, 25, 26, 27, and so on, yeah. So you count to the east, you would go higher in longitude, because we're going east to west, and then going to the west, you would get lower in longitude.
Okay.
Yeah, so you can just say it's at about 25 degrees longitude.
Okay.
And, the way they formed this whole Mare Serenitatis is a giant impact basin So very early when the surface of the moon just started to solidify, but it was still, the crust was still very thin and then the magma underneath was still very hot. And that was early in the solar system, when there were still very big chunks, asteroid-sized chunks, moving all around among the planets. So there were very violent impacts. And, the crust of the moon, because it was still so thin, and on the near side it was thinner than on the far side, it broke through the crust. There were a lot of cracks, and then lava came up from underneath and seeped through the cracks and filled in this impact basin. And then, of course, because, it covered up all the existing craters and got smooth, and solidified in a smooth surface texture. But of course, it didn't cool all at once in a snap. The cracks were probably deeper in the center of the basin, so that's where the lava came up first, and then it sort of pushed to the edges. And of course, at the edges, it started cooling more because, in the center, more lava came pushing up from underneath. And then, the new lava then kind of flowed and pushed against the old lava that was already cooling. And that's how we believe wrinkle ridges may have formed, because you have a whole section of lava that's already starting to cool, and that is pushed further out by new lava that's coming up from underneath. And then you get this, kind of like in a pudding, like a wrinkle in the pudding skin or something like that. So that would be how the wrinkle ridge, definitely lava that's been cooling and being pushed further out, that type of thing.
Okay.
And then in number 7, that goes back to, well, it's a giant circular basin, essentially. It's a lowland compared to the lighter gray colored highland around it. So, the smoothness, the darkness, and the low-lyingness of the mare would, make it appear to have formed by, lava that has filled it in and solidified.
Where would we examine the image of the menorah?
Oh, yeah, the crater?
Yeah.
Yes. Actually, if you go from the wrinkle ridge, if you just go right,
oh, it's right
to
there.
the east,
It's right there.
Yes, it's right on the 30-degree longitude line. And it is kind of hard to see because what seems to have happened to it? If we compare, for example, Le Monnier or Le Monnier, this crater with the one above, further to the north, Posidonius. How are those two craters different?
That one seems to be covered fully.
Yeah, if we look at Le Monnier, then we only see a crater rim on the eastern side, on the right side, but there's no crater wall or crater rim on the western or left side. So, it really looks like the crater Le Monnier has been there, but then, that giant impact that formed the mare came, and the lava from that mare has sort of flooded into the crater, totally taken down the western crater wall. So in that sense, we could conclude that, well, that's sort of evidence that the mare comes from, well, lava activity or volcanic activity, because it had, the lava that seeped up through the cracks washed over and dissolved the western crater wall of Le Monnier and totally, flooded and leveled it out.
Okay. Well, how about 12?
Yeah, shall we continue with the craters?
Oh, you wanted to I'm sorry?
Or, yeah, did you want to continue? I didn't quite understand.
Oh, we could. I just thought that I could skip that one, but it's fine if you'd like to go ahead.
Oh, with the craters? So you're pretty comfortable with the craters?
I haven't, that part I didn't do yet, but it doesn't look like it's too hard.
No, I mean, it shouldn't be. It's pretty self-descriptive. You know, if you look at the profiles that are given, you know, we could even look in this image. Basically, you're looking at 3 different crater types, and you know, one crater type is flat-floored, and the crater Le Monnier would definitely be flat-floored. In this particular image, I don't see any other flat-floored crater. Well, maybe this one down here, Vitruvius or something, that is large enough to be flat-floored, or this crater, Litro, I don't know if that's the name. You know, so you just see a crater wall, and then inside the floor is entirely flat. And you know, actually looking at Posidonius, it looks like it's pretty flat-floored too. It's just that, you know, since it's an older crater, since then a new little impact has occurred right smack in the center of it. Let's see, and then the, well, flat-floored Central Mountain Peak. Actually, we don't see one in here. Maybe I can just go to, well, here at the bottom, Plinius. You know, you see it's sort of a slightly larger crater, but then in the middle there's sort of like a little central mountain, and that is a rebound feature. So the impact liquefied the lava, you know, so much that it got first pushed out, and then you know, when the energy had dissipated, it came back and sloshed back, kind of like when you have a water drop and you look at it in the time lapse. You see how a water drop hits a water surface. You know, first it pushes the surface away, but then it sort of also combines with the surface, and because of the surface tension, it rebounds then and forms like a central peak. You know, except with the water stays liquid, but with you know, rock that is exposed to cold temperatures of space, you know, of course it starts cooling throughout the entire process. So by the time it rebounds, you know, it solidifies the mountain then in the center, where I have my little plus sign over. So the flat-floored and the flat-floored Central Mountain Peaks, they're usually the larger craters, and then the bowl-shaped craters, you know, which look like somebody took an ice cream scoop and scooped out a little bit of lunar soil. They would be the smallest craters, and you can see sort of like a semicircular shadow on the floor, and that indicates, you know, that it's sort of scooped out. So this one here would be a good example for a bowl shape, or, you know, any of the smaller Posidonius craters would also be good examples for bowl shapes. Yeah, so that's pretty much like a summary about the 3 different types of craters. Also, well, really quickly, have you been able to locate Copernicus on the worksheet, the crater Copernicus?
No, I have not.
Okay, it's actually, on the worksheet, it's pretty easy to locate because there is this bolded, fuzzy-edged circle that is sort of, you know, in the middle, but towards the upper left. Okay, yeah, that's the crater Copernicus. So you can put a little C in there on the worksheet.
Okay.
Yeah, and I'm going to go to the next image now because you're... Okay, well, let me just say one more thing because we're recording this. Let's see, when you look at the... Oh, okay, that's the close-up of Le Monnier. You're just trying to get to the correct image. Okay. Okay, the image labeled moon map, that's the one where you want to look for the different shaped craters. So, the image labeled moon map. Yeah, just for, recording purposes. So this is the image that you want to go to pick craters of the different shapes, the flat floor, the flat... Say again?
Is your screen open?
Yes, I'm looking at I'm looking at a section of the moon map now between 10 degrees west and 10 degrees east, and the 0 longitude line is going straight down the middle. Maybe
there's a message across my screen that says network error, timed out.
Oh, let's see. Could you refresh if you hit the refresh button? Can you still see my screen? Kamari, can you still see my screen?
Hello?
Hello, can you still see my screen?
Yes, I can see it now. I'm sorry, when I refreshed it, it just hung up. It hung up.
Oh, okay. Yeah, I just switched to back to the map. Can you still see it?
Yeah, I can see that now.
Oh, okay, good.
But
Okay.
if it happens again, I'll just listen to you because I think the last time we did a Windows session, there was something I wasn't seeing, but the next time when I replayed it and just watched it, everything was shown. So I think my computer can.
Okay, all right. Okay, so yeah, this is the moon image where you're supposed to look for, the 3 different types of craters. I just wanted to show that before we go on to the next image, because I talked about examples on a different image, just as an example. Okay, so yeah, we were just talking about Copernicus. So now we want to look carefully at the image labeled Copernicus. So we're gonna, and I'm sorry I have to take this detour across the title screen of that module every time so that it goes back to the images. Okay, so we're gonna go now to the image of, let's see. Okay, so we're going to be actually looking at 2 images. We're going to be looking at the photo that was taken by the Apollo 15 command module. And it's actually the crater in the foreground is not Copernicus. The crater here at the edge is Copernicus. See, that's why that is bolded in question 13. So the large crater to the far right near the horizon is Copernicus. So that's this one over here. And that means you want to identify, which crater this is. But what we can do, we can compare this shot and look at a map that shows Copernicus. and it's this one right here. So this is the image labeled Copernicus. So we can see Copernicus here. And, you know, we need to figure out, okay, since we're seeing it at the edge of this picture, you know, that picture must have one of the craters that are surrounding it in the center, or, you know, as the main part of the image. And, well, I mean, let's see which ones we have to choose from. You know, there's something down here, but that is more like a large and a small crater. And, you know, then we have this one over here, you know, which is a pretty good sized crater. It has a little mountain in the middle, so that would be an example of a flat-floored central mountain peak. Well, over here we just have mountains. We don't really have a crater large enough. You know, they're just some smaller ones. So I guess, you know, we have to make up our mind, okay, the crater in the center of the image, you know, is it the one on the bottom left, which has a sort of like a double crater there, or is it the one on the upper right that has sort of like a mountain range around it?
What about the one like directly above Copernicus, like straight ahead?
This one?
To left. That one.
Oh, well, this is Copernicus. That is the crater that's at the right edge of the image.
No, not that one. Like if you move them out,
this one?
If you go straight along that line above that one.
This one. Well, I mean, we can see. So if we look at this crater here, then I mean that's definitely in a mare. So we wouldn't. I mean, if we look at this photo, we shouldn't see any mountains around it. You know, it should be smooth and dark. So let's see. So we want to look not just at the crater, but also, you know, at the area surrounding it. Okay, so we go back to the MoonLab images and to the photo that's labeled Copernicus. Well, I mean, what does it look like to you in terms of the terrain that's around it? I mean, would you? Oh, I just apparently enlarged it, which is probably a good idea. I mean, does it look very smooth to you, or more a little bit mountainous?
Mountainous, I would say.
Yeah, I mean, it does look like, you know, there's sort of like a mountain range that is right at the edge here, and then sort of wrapping around. And there are only very small craters around it. And the only thing that separates, you know, the crater that we need to identify from Copernicus at the right edge of the image, you know, sort of like a squiggly line, you know, right here. So a little bit rough terrain, but then also this line of something or other. So let's go back to the map view. Let me also enlarge that a little bit. The Copernicus. See, if you go down, so the one that we were first looking at, you know, we didn't really see a double crater. And if we see Copernicus at the edge of the image, then, you know, we should have seen if there was like a larger and a smaller crater together. But we didn't really see a larger and a smaller crater. You know, we just saw this one large crater. It was a mountain range, you know, and some squiggly line in between. You know, if we look at the other crater here, I guess that was Lambert. You know, we would have expected to just see smooth terrain around it, you know, but we didn't. there was sort of a little bit of a mountain range. Yeah, it's this one with a really long name, and unfortunately the name is sort of cut off. Then it's Eratosthenes. So after the E, there should be an S. Kind of a mouthful. Because if you can see, we'll go back to the image, but you have the mountain range, to the north of it, and then also sort of to the east of it. And then, we have this line of, it's actually a line of sinkholes here in between, and then we have the crater Copernicus. So let's go back to the image. I'm going to pick the picture. See, and here you see the northern mountain range. And here how it wraps around to the south, I guess, and then in between, if you go from this crater here, which we think is Eratosthenes, over to Copernicus, we come across this squiggly line of sinkholes. So that's a pretty good fit. Everything that we see in the image, we can also see in the map. And there's nothing here in the image that is not also shown on the map. So I'm going to go back to the map now. See, let's enlarge that a little bit again. Because another question is, well, which direction are we looking? So, once we have identified the prominent large crater, which was Eratosthenes, well, we're looking sort of from the direction of Eratosthenes towards where Copernicus is. So if you're a person standing in or on the wall of Eratosthenes looking towards Copernicus, then you would be located in what compass direction, looking into what compass direction? Those are the other two blanks.
Northwest.
Yeah, you're in the northeast, so you're looking from the northeast to the southwest.
Oh, northeast to southwest.
Yeah, so the top is northeast, and then you look towards Copernicus, which is southwest of where you're looking. Okay, yeah, maybe we can cover the next few questions sort of like in a little summary. It's asking about the long jumbled slope on one side of Eratosthenes. And, it looks at the impact, the meteorite that hit there and caused the impact sort of hit at an angle, that it plowed into the mountain and sort of pushed it out a little bit. Because, we see this slope on the western side of Eratosthenes, but not on the eastern side. And then it's asking account for the appearance of the long jumbled gradual slope. Oh, wait a minute, we just did that. Oh, yeah, if we go back to the photograph, so that for question 16, we want to look at all the little craterlets in the foreground. So let's take a look at the photograph again. And this time we're not going to zoom in because we're interested in these guys here. So how do you think they formed? That you have like a handful of little small bowl-shaped craters, you know, just behind the mountain range that we think the impact pushed out.
Those are like the younger ones that came from the center.
Yeah, sort of. I mean, they're not much younger, but what we think happened, you know, when the impact occurred, because it was at such an angle, you know, that pushed not only the mountainside ahead of it, but then it also in the same direction, because that's the direction in which the impact occurred, you know, it exploded, and material from the explosion was flung out, and because, you know, it was much smaller pieces, much lower energy, you know, they sort of were flung out ahead of it and caused smaller impacts. You know, those would be the craterlets. And you see that all over the moon's surface, you know, with the larger craters that formed more recently. You have like a whole bunch of little craterlets that are scattered around it, you know, that are caused by debris that was flung out in the explosion when the impact occurred on the surface. So they're like secondary craters. So that would be number 16. And then number 17, there's a winding line of small craterlets, and that's now the squiggly line here. You can actually see it better on the map, so we'll go back to the map. Okay, I'm going to zoom in a little bit. Now right here is sort of a line, this is the squiggly line of craterlets. Well, how are they different from, you know, these bowl-shaped craters that we've seen? You know, Eratosthenes E, D, C. How are they different?
I can't really see the C, D, and E.
Yes, you remember from the image, you know, from the actual picture, they were like, you know, random bowl-shaped craters. You know, they were sort of.
Oh, those. Okay.
Yeah. I mean, do these look?
On the right. The other ones were more spread out. Seemed like they were scattered anywhere, but these have like a trail going on.
Exactly. You know, they look like they're in a trail. They're sort of in a line. You know, like pearls on a string or something like that. So there definitely seems to be, you know, they're lined up in a specific way, whereas, you know, the other craterlets, they were just sort of randomly scooped out. So that would be one difference. And yeah, another one. Well, if you look at them, I don't know if we can even, no, it's just this one. Well, do you actually see crater walls? You know, they don't really have walls, you know, that go up. Like if we go back to, let me go back to the image, the photograph. You know, so these craters here are the Eratosthenes B, C, D, I don't know, maybe even A. But you can see that, you know, they have a crater wall around them. You know, the sun comes from the upper left here. You know, it shines on the wall where it rises up, you know, and then in the back you can see the wall even casts a little bit of a shadow. So these craters definitely have a rim, you know, that sort of goes up above the general surface area. And if we go back to the map, and zoom in a little bit, you know, they don't really have a crater rim that goes up, you know, and sort of outlines them. So these craters that are in a sinuous or wavy line, I mean, they are of a different nature than the ones, you know, that were thrown out as secondary craters from the impact. And then if you think of another like wavy feature that we looked at before, you know, the wrinkle ridge, what kind of surface process formed the wrinkle ridge?
The wrinkle were at the top, and they look like they kind of went around in a circle.
Not quite, but it was sort of, you know, lava that was cooling and spreading out.
Oh, how they were formed.
Yes, how it was formed, and then, you know, fresh lava came and pushed it, you know, a little bit faster so that it formed wrinkles, and it was also a little bit wavy. It wasn't exactly straight. So it was lava, and that's actually the same thing that you have here, you know, where you had the surface already cooling, but you still had lava rivers that kept flowing underneath the surface. Yeah, and then when they ended, then the surface sort of, you have sinkholes. So those are basically sinkholes in an underground, that what used to be an underground lava tube or an underground lava river. You know, so that's how they would be different. You know, we say volcanic, even though there are no volcanoes on the moon, but because they were formed by flowing lava, you know, that's why we say volcanic. So they would be formed by flowing lava or of a volcanic origin, you know, whereas the random ice cream scoop bowl-shaped craterlets, they were due to impact. Okay, so that would also cover question 18. Okay, and then question 19 talks about rays. You know, rays are light streaks radiating from craters. Name a crater with extensive rays. And you can see rays actually from Copernicus itself. You know, that's sort of the whitish, very fine whitish dust that radiates out. It's also part of the stuff that is thrown away by an impact explosion. It's you know, part of the ejecta, what is ejected. But yeah, you cannot see it that well because other craters, you know, have sort of interfered a little bit with those rays, and you know, in the light-colored mountain ranges, you can't see them as well. Yeah, let's go back to the moon images and see if we can find another impact crater with nice rays. What if we look at this image? Well, I suppose Copernicus was still better than any of those. So in the face-to-face class, the students can look at the entire map. You know, we just see sections of it. I was looking at another one. No, we don't see any nice rays here either. Actually, if we go to the near side with labels, we might be able to see one. Well, I mean, I guess in this view, you can see that Copernicus does have visible rays radiating away from it. You know, so that would be one choice. Let's see if we can find another one. Well, there's one I remember by name, but it might be on the far side. You know, Tycho, who was named after Tycho Brahe. That has very nice rays, but I'm not seeing it right now.
What about the one on the right?
Yeah, this one here?
At the bottom, yeah.
Yeah. Yeah, I suppose that's the Venus. Yeah, that looks, yeah, unfortunately I cannot zoom in any further. But yeah, I mean, that, you can see some rays, you know, some whitish dust that is thrown out by the explosion. Yeah, Tycho must be on the far side. Let's take a look at this one here. Yeah, let me go back to the moon images. So yeah, I guess we've identified two that could work. Yeah, here's the far side of the moon. I don't think we have the far side of the moon with labels, but this one definitely would qualify as an impact crater with rays. That might even be Tycho, or maybe this one up here. You know, you can see because the far side has fewer impact basins, like the Mare. You know, you can see the rays, craters with rays a little bit better. You know, also like this one here. You know, how the rays are radiating out from it. Okay, yeah, let's go on. It asks in question 20, give 3 reasons why you wouldn't find rays like that on Earth. And you sort of want to think about, well, what different surface conditions do we have here on Earth, you know, that are different from the surface conditions of the moon? Well, for example, what do we have here on Earth that doesn't even exist on the moon? I mean, one reason why go ahead.
I said water.
Yeah, water is one reason. You know, if you look at Earth's surface, actually 75% is covered in water. So there would be no way we could see rays. You know, if an impact occurred on the ocean floor, you know, there wouldn't be any rays. And pretty soon the ocean crust sort of recycles, so pretty soon we wouldn't even see that impact anymore. So water would be one. Well, what else? I mean, what is another reason why the astronauts need to wear a spacesuit on the moon?
Oh, oxygen level.
Yeah, oxygen, air. So there's no atmosphere there, no weather. So you know that would be another reason. So no wind erosion, no water erosion. Well, I mean, if you look at the moon, you know, the soil there, or actually you wouldn't even say soil, the dirt there is pretty bare. And if you look at the Earth, it's only bare in some places, but in other places, what do we have here on Earth? You know, like if you look out the window, what's covering up the bare ground in your, yeah, grass, trees, you know, we have vegetation. So, you know, the vegetation itself is, you know, growing on top of the soil and whatever features are underneath. So they're covered up, so you wouldn't be able to, you know, see these rays because they might be covered up by forests or prairies or, you know, cities and stuff like that. So those would be some of the reasons you could say. Yeah, another reason would also be, you know, that the gravity on Earth is 6 times stronger than on the moon. So, you know, if there were any stuff thrown out by the explosion, it wouldn't go so high and it wouldn't go so far. So that would be yet another reason. Okay, and then the next section is about rills and faults. And here you basically want to distinguish between two types of rills and faults. We've looked at the wrinkle ridge, for example. That's a type of fault, and we've also looked at the line of craterlets. The sinkholes of the lava tube between Copernicus and Eratosthenes, and those were wavy and or also sinuous. The lab manual says sinuous. So they're not straight, which is an indication that they were formed by lava, so volcanic activity. But then there's another group of faults and rills. Rills are basically narrow ditches, and those are straight in nature. Now the really ruler straight features, they're formed by tectonic activity. When the crust cracks in some places or settles, and the moon doesn't have plate tectonics or anything, but still when it was forming and the crust cracked, for example, in places where it didn't break and you didn't have lava seep in from the impact, but you still had crust cracking, those would be straight cracks and not curvy. So that's how you can distinguish the tectonic features from the volcanic features. And there's an example here, the Alpine Valley near 50 degrees north and 0 degrees longitude, and the straight wall near 20 degrees south and 10 degrees western longitude. So let me go back to the images. Okay, let's see. Here, for example, the Alpine Valley. Fairly straight. It doesn't really look narrow. It doesn't really look sinuous. And another indication, that this is not volcanic, is that it's in the highlands actually. So especially, through here, like a mountain crack in the mountain ridge. So because it's straight, we would actually call this more of a tectonic feature, and because it's also located more in a mountain range. It looks like when those impacts occurred, well, maybe at that point, the crust was just sort of cracking open, but it's definitely a crack in the crust and not a, lava flow feature. Okay, and I'm wondering if we can also see those on the map. If we look at this map here, for example, and we look at a mountainous region, right around here are some faults, and then right here, if we zoom in on this, we find this straight rill also cracking through the mountains. So you could put that one down as an example for number 21.
Radius mile.
Yeah. I think the word rill actually comes from the German.
Oh, rill. I'm sorry.
That's okay. Yeah. Because in German, I happen to be German. We say Rille as a narrow, ditch. So that's a word we would use. And I guess way back when they came up with all these geological terms, the Germans were like at the forefront of geology. So that's how a lot of German terms were incorporated. Also, for example, the term mantle comes from German. It actually means coat, like like a thick winter coat. So that's where the word mantle comes from. But anyway, yes.
Okay.
Yeah, and that maybe if you think about it that way, it actually you can remember it more easily than just thinking, oh, that's who knows who came up with these letters or expression. So yeah, mantle is a very thick winter coat.
I remember too, because my mom used to get them for me all the time when I was a little girl. I hated them.
What, the thick winter coats?
Yeah, because they looked so boyish. They weren't girly.
Yeah, I guess it depends. If you of course have a full fur coat, maybe that would look more girlish. But I know. Yeah, those ski, those imitation ski jackets, or yeah, I don't know. Yeah, I don't care for those either. And then, I'm already a little bit fuller to begin with, and if I have a fuller winter coat on, then that looks double full. So I don't need that. Anyway, yeah. So you could put that down. The Ariadeus. I don't even know how to pronounce it. I know how to pronounce Rill. So you can put that down for for question 22. Okay, and then suggest how they formed. That's how you can talk about the cracking of the crust. So it would be more of a tectonic process rather than a volcanic process. Okay, and then if we look at photograph B, let's go back to the moon. That's the next question over 23. Let's see, that's right here near the bottom. Okay, this is photograph B, and that was also taken by Apollo 15, and it features two sinuous rills as well as a long oval depression and numerous craters. So, you can see one sinuous rill here, and you can see another sinuous rill at the upper right edge of the image. Okay, the first sinuous rill was on the left edge of the image. And then here is an oval depression, and then, like a whole bunch of little craters. So in 23, with the exception of the lower right of the photograph, so the lower right of the photograph, is this one. But if you look at this, most of the area of the photograph, then what kind of terrain does it look like? I mean, does it look more like Maria, which is darker in color and more, lower lying, or does it look like the highlands, which is more mountainous and lighter in color?
Maria.
Yeah, it is darker in color. So, and overall, of course, it has tons of smaller craters here. But, if you look at the general surface texture, it seems to be smoother. It doesn't look mountainous or anything. You don't have any ragged, jagged mountains. Like, for example, on the lower right here, oops, sorry, I didn't mean to do that, which was the exception. Here you have lighter colors, and the terrain itself seems to be more hilly and mountainous. So that means the majority of the image, we're looking at Maria. Okay, and then number 24, the craters in a string near the center of the photo are like those of question 17. Thus, they are, like if you look at those craters here in a string towards the center, so what kind of process has formed these craters? If they're all in a string and they don't have any crater walls, they were formed by lava flows, so they would be sinkholes in a lava river that was flowing underneath. When the river stopped flowing and supporting the structure, then the sinkholes occurred because, you have other craters, impact craters, so they're little moonquakes, and if everything cools off and becomes brittle, then you get these sinkholes forming. So that would be a volcanic process. And again, we're also looking at the mare, and we're looking at the two sinuous rills here, and whenever we're talking about sinuous, wavy features, then what kind of process are we looking at? And the choices we have is impact, tectonic, or volcanic.
I'd say impact.
Well, if it's wavy, for example, we're looking at the wavy rills here, where you probably had...
Oh, volcanic.
Yeah, it's volcanic. You had lava flowing on the surface in these rills, whereas it was flowing underneath the surface where it then, collapsed. So yeah, definitely volcanic. Okay, and then actually question 26 is sort of like a summary question, where you go back and look at different features and then, just note whether they were formed as impact, tectonic, or volcanic, or a combination. So that's sort of like a review of the features covered so far. And then the very last section of the lab is the relative dating. So let's just take a quick look at that. Okay, and relative dating in general is essentially, it's the opposite of absolute dating. Absolute means you can assign an absolute age to something. You would take a sample of a rock and then measure its absolute age by radioactive dating, for example. That it is around 3.9 billion years old. That would be the ages of the rocks found in the mare. And if you pick up rocks from the highlands, that's what the astronauts did in bringing them back to the Earth and subjecting them to radioactive dating, then you would come up, highland rocks would come up as, 4.2 billion years. So that would be absolute dating. You can say, okay, that's their actual age. But relative, instead of an actual age, you would only be able to say, okay, that feature is younger compared to that other feature that is older. And I think I have a slide in there of a tire track in a mud puddle. And basically, if you have a mud puddle that is nice and muddy, and then you have a tire track that runs right through it, and then the whole thing hardens up, then you can sort of say, oh, and while the tire track is hardening, somebody steps across the tire track with a footprint, then you would see that the footprint is on top of the tire track. So the footprint would be undisturbed and pristine. You could see the whole thing. But the tire track would be disturbed by the footprint. So you'd see tire track and then the disruption of the tire track by the footprint, and then you'd see the tire track continuing. So you could tell, that the footprint was there after the tire track, because you can still see the footprint hole, and you see it on top of the tire track, which has been disrupted. And then, of course, the tire track itself disrupted the mud puddle. So you could sort of say, okay, the mud puddle was there first, because that's what the tire track imprinted into, and then, but the footprint was the youngest because it disrupted the tire track. So that's sort of relative dating, where you say, okay, this feature is younger and this feature is older. So generally, the younger features are on top, and the younger features are undisturbed or less disturbed than the older features. Okay, and then let's go to the moonlight images and look at, let's see, I think there is an image way at the bottom that is called relative dating. Okay, we're looking again at Copernicus. We're looking at Mare Imbrium. And we also need to find Cassini A and B. Let's see. See if they're on this image. I don't see a scroll bar at the bottom. Maybe I have to zoom back out and then zoom back in on a different. Oh, there they are, right at the edge. Okay, here we have Cassini. So Cassini would be the largest crater here, and then Cassini A would be the one that's smack in the middle. Okay, so you're supposed to determine the relative age of Mare Imbrium. Cassini, Cassini A in the middle here, and Copernicus. And you're looking at pairs of them. So, for example, the first pair you're looking at, and you want to determine or circle which pair is older. So if you compare Copernicus and Mare Imbrium, let me zoom out for this. So Copernicus down here, with its rays, and then Mare Imbrium, which one of those is older? So if you think of, Copernicus's rays showing up on top of Mare Imbrium.
So Copernicus is the older?
Well, would it have been possible for Copernicus' rays to be visible if Mare Imbrium was younger? Because it means Mare Imbrium would have formed after Copernicus. And, since it was lava seeping up and filling in the whole thing, it would have obliterated the white, the white dusty lanes of the rays. The rays are very light, whitish dust. So it would have easily have been disturbed, dissolved and covered up with lava. So actually the Mare must have been there first and have solidified, and then Copernicus must have formed later, in order for its streaks, its rays to settle, and stay and sort of paint the Mare with its rays. So you'd say the Mare is older. See, and then we're also looking for Archimedes. So Mare Imbrium would be the whole thing. And then we have Archimedes here. Well, it's actually a little bit, this one is sort of a case where you wouldn't, it's not quite clear. Well, you do see follow-up ejecta here from Archimedes D, Archimedes C, G. So that probably means Archimedes would be younger than the Mare because we can see the secondary impact. Oops, I'll drag that again. Probably, the Mare was still fairly young when the Archimedes impact occurred. But the fact that we see the follow-up impacts of Archimedes A, B, probably further out, means that the Mare must have been there in order for those smaller craters to form. Because if the crater and its little ejecta secondary craterlets would have been there first, then those craterlets for sure would have been covered up when the Mare formed. So the Mare must be older than Archimedes. But if we look at the Cassini situation now, well, my family's playing video games in the background, although they should be going to bed. But I guess that will be a little bit later. We're just wrapping up here. So, if you look at Cassini, even though the craters around it are labeled Cassini B, Cassini A, and Cassini M, you wouldn't have any secondary impacts inside a larger crater. So they have probably only been labeled Cassini A and B because they're smaller craters that are, really close to Cassini itself. And also, if you look at the crater wall of Cassini, that looks a little bit similar to the crater wall of Le Monnier that we were looking at earlier, that had been overrun by lava from when the Mare formed. So it actually looks like Cassini is older than the Mare, that when the Mare formed, that the crater walls of the original Cassini crater were compromised, or some of them were compromised, right here where the crater wall is gone. But at the same time, if you look at Cassini A being like a nice bowl-shaped crater, that must be younger than Cassini because Cassini is a bigger impact. So if Cassini A had formed before Cassini, and then the Cassini impact had occurred, that would have obliterated Cassini A. So any crater, also Cassini B, if we look at Cassini B, that is also smaller and bowl-shaped, that would have also been destroyed if a larger impact like Cassini would have occurred afterwards. So in this case, we would say that Cassini is older than Cassini A or the Mare because Cassini has been affected by, or has been changed from its original shape by the Mare and also by Cassini A. So this is sort of the thinking, and similarly for the last question, which we don't have to go over in detail, but you're going to do the same kind of thinking and apply to the last image, which is again image B. And you're going to look at the Maria, the long oval depression. So this would be one of the objects to look at, the long oval depression. The small round craters in the depression. So there would be this one here. Any of those, there's little small round craters in there. The less sinuous rill. and the mare, whose edge can be seen in the photo. So those 4 objects you want to compare and then list in order from, let's see, of age. So which you want to start with which you think is the oldest one, and then look at them. So the long depression, the small craters inside the depression, this one, any of those, the less sinuous rill, and the mare, which is the main part of the image here. So these 4 features you want to list in order from oldest to youngest. All right, well, if you don't mind, I need to wrap up and get my kids to bed. My husband is playing video games with them. Yeah, and he enjoys those video games just as much as the kids. So are you pretty much okay with the remainder of the lab?
Yeah, I think I will be. I'll have to review a lot more terms. Like I said, I'm only taking the lab to this course, so I don't have the other ones. So I have to always review terms to understand what you mean, because some questions you're asking, I didn't know the terms, but if I keep on the lab over to get it correct, I'll be able to understand it better. But I think this is very thorough.
Yeah, you could go back, look, I'm going to save this, and, you can go look at the archive. You can also, while you're working out individual questions, just send me an email about, question number this, I'm still a little bit confused on. So you can just send me emails about individual questions then when you go through them.
Okay.
All right, I'm going to stop the archive. And